Under a tapestry of unfamiliar constellations, a red twilight settles across an ocean world. Two moons, arched in slender crescents, cast faint, rust-hued reflections on the slow-moving tide. The sun, a long-burning ember in the sky for weeks, has finally dipped below the horizon, and with it vanishes the oppressive breath of summer. Now, the world is lit by a sky choked with tens of thousands of stars. Above the curved silhouettes of the twin moons, a single point of light flares brighter than all others. A celebration erupts across continents. These people know what this is. For them, this is tradition. This is a guest star, a supernova, yes, but dressed in older language. And yet while crowds gather in joy, a single observer watches in horror. Satellites report a catastrophic dip in atmospheric ozone. The star is not just bright, it is close, too close. Within a week, the sky will turn from guardian to executioner. Had such an event struck Earth, the result would be the same mass extinction. But this is not Earth. This is a world that bloomed and burned out when our universe was young and restless. Galaxies were still embryonic. Starbirth exploded across cosmic neighborhoods, and death came just as swiftly, with each detonation of stellar grandeur bathing space in radiation and violence. These were the nursery days of worlds, and the cosmos was both generous and brutal. What kind of planets emerged in those early fires? What strange cradles of matter gave shelter to the first sparks of life, if life dared to arise at all? Not long ago, imagining the existence of worlds beyond our solar system was pure speculation. That other stars might host planets like our own seemed logical, but unprovable. Today, not only do we know exoplanets exist, we know they are everywhere. Thousands have been confirmed, tens of thousands are suspected, and still, we have only scraped the faintest frost from the tip of the iceberg. Many of these planets defy our imagination. Some are vast gas giants, clinging to their stars at blistering distances, their atmospheres whipped by winds that carry molten glass. Others are giants darker than coal, absorbing nearly all light. There are ringed behemoths with halos spanning hundreds of millions of kilometers. There are scorched earths that glow from tidal agony, and frigid wanderers cast adrift in the darkness between stars. And somewhere among them may be the quiet ones, the blue marbles tucked into gentle orbits, wrapped in atmospheres thick with nitrogen, traced with water vapor and carbon dioxide. These are the ones that might breathe. To find them, astronomers devised clever methods. They measured the trembling of stars, tugged by the invisible pull of planets. They watched for dimming starlight as planets passed in front of their suns. They listened for the rhythm of pulses from dead stars whose consistency revealed the gravitational fingerprint of orbiting bodies. Even from hundreds or thousands of light years away, they hunted the specters of alien skies in the contaminated light filtering through thin planetary atmospheres. Their discoveries painted a cosmic gallery more diverse than anything we had imagined. In some systems, planets dance in tight synchrony, so close their days are measured in hours. In others, twin suns rise and set in surreal choreography. Rocky worlds orbit dwarfs, giants, and even the burned-out cores of long-dead stars. Some have rings wider than the Earth-Moon distance. Some are little more than exposed cores, their outer layers long since torn away. One of the earliest detections came from a pulsar, a dead star spinning with unimaginable speed, sweeping its surroundings with radiation. There, two worlds clung in tight orbits. Later, we found gas giants hugging their stars at impossible distances, far closer than Mercury sits from our Sun. These hot Jupiters, bloated and strange, were not what we expected, but they were easy to find. Their very improbability made them visible. Eventually, we found smaller planets, some not much larger than Earth, some orbiting within the so-called habitable zones of their stars, worlds like Kepler 186f and K2 18b, where hints of water and complex molecules in the atmosphere make astronomers lean closer to their telescopes. With each detection, we come closer to answering a question that has haunted us since the beginning. Are we alone? But even as we look forward with new missions, with the James Webb already reshaping what we thought we knew, and the Habitable Worlds Observatory preparing for a launch that is still decades away, we also look backward. How early did planets form? How fast did the cosmos learn to build homes for life? The universe wasted no time. The first stars formed within a few 100 million years after the Big Bang. Born from pure hydrogen and helium, they lived briefly and died explosively. In their deaths, they forged carbon, oxygen, silicon, the stuff of planets. The next generation of stars inherited this enriched matter, and with it, the ability to form rocky worlds. One of the oldest known stars, TOI 561, is over 10 billion years old. Around it, astronomers found a super-Earth, not gas, not vapor, but rock. Somehow, in a cosmos still young and under construction, a planet of solid matter took shape. And what of life? The record on Earth is suggestive. Life began as soon as the conditions allowed. Perhaps that is universal. Perhaps the moment a planet is stable, the moment water pools, chemistry stirs to life. If that is true, then there may have been civilizations' entire histories rising and falling before our solar system even existed. Of course, survival is another matter. The early universe was not kind. Supernovae were common, their death shouts loud and lethal. Galaxies collided more often. Radiation bathed entire regions. But life, if it had shelter, might persist. On moons buried under ice, in oceans shielded by thick atmospheres, in caves lit by the slow churn of geothermal warmth. The first exoplanets may have orbited dead stars. Some may have been born again from the debris of supernovae. Planets can survive where stars cannot. And life, stubborn and secretive, may have found ways to persist. Today we know of planets that orbit twin suns, planets with diamond crusts, planets of endless storm, of lava, of ice, of hydrogen oceans, and super-Earths with thick atmospheres where pressure might allow strange chemistry to unfold. We know of rogue planets that wander the galaxy alone. And still, we are only at the beginning. Even in our own solar system, we have yet to exhaust all possibilities. The Kuiper Belt, that distant ring of icy remnants, is home to ancient relics like Arakoth, small, cold, and unassuming. It remembers the solar system's birth. There may be billions more like it, the foundational debris from which planets are made. Worlds can begin as dust and ice, growing slowly or not at all, lingering at the edges of starlight. If such objects formed early, and survive the fires of stellar adolescence, they might persist for eons, untouched and unread, like forgotten pages in a cosmic archive. And if one of those pages held life, if one of those icy worlds or buried oceans gave rise to consciousness, then perhaps they looked back. Perhaps they saw us, a pale blue dot circling an ordinary star, lost in a spiral arm, and perhaps they wondered if they, too, were alone. But we are here now, looking out, reaching, listening, and with every new discovery, we find that the universe is more generous than we dared hope, that planets are common, that diversity is the rule, not the exception, that life, if it can arise, might have had countless chances. The stars are full of secrets, and somewhere out there, beneath another sky of moons and fire, a new guest star may already be rising. The stars had begun to rise again over the quiet plains of a distant world. Its surface, pitted and ancient, bore the scars of countless impacts. Above, the twin suns had long since dipped below the horizon, and a sharp chill settled in their absence. Yet the sky was anything but still. Constellations stretched across the heavens in impossible patterns, lit not just by the ordinary stars of their galaxy, but by something else, a guest star, radiant and terrible, still pulsing with the residue of a titanic death. The people of this world had celebrated its arrival with fireworks and song, yet some had known the danger. Some had read the warnings, and when the sky dimmed not because of the night, but because of the ruin spreading through their atmosphere, they understood too late. We are not so different. We too live under a sky that holds both wonder and threat. We too reach out, seeking signs that we are not alone, that others have survived, even thrived. And in that search, we have begun to find them, not life, not yet, but the homes where life could dwell. The first signs came not from places of comfort, but from the strangest of sources. A pulsar, dense as an atom and spinning with the rage of a collapsed sun, pulsed its radiation with mechanical precision, and then a stutter, a hesitation in its rhythm. That hesitation revealed the gravitational whisper of planets, unseen but undeniable. They were dead worlds orbiting a dead star, but they were worlds nonetheless. It was the beginning. Then came the hot Jupiters, giants too close to their stars, their atmospheres churning, their orbits defying logic. They were not like anything in our solar system, and that made them all the more visible. Then came the others, worlds dark as ink, their surfaces drinking in all light, worlds of glass storms and cobalt skies, worlds that glowed from within, torn by tidal violence. The catalog grew. For a time, it seemed as though the universe favored the strange, the wild, the inhospitable, but the tools sharpened, and the surveys deepened, and we found more. Super-Earths, mini-Neptunes, worlds with gentle orbits and familiar sizes, worlds where water might pool and air might linger. We found systems of harmony and chaos, planets circling binary stars, moons the size of Mars, rings wider than the sun. And still we only saw the beginning. The techniques improved. We stared at stars, waiting for a tiny eclipse. We listened for the tremble in starlight. We parsed spectra, finding fingerprints of molecules in the atmospheres of alien skies. Each method, refined, revealed more. Kepler stared at a patch of sky and found thousands. Tess widened the gaze and found thousands more. And with each new telescope, each new mission, the flood continued. Not every discovery was dramatic. Some were quiet, some were strange, some were beautiful. A world called Phoenix clung to its atmosphere against all odds, orbiting a dying star. Another, Kepler 16b, circled two suns in an echo of a galaxy far, far away. One planet shone deep blue, not from oceans, but from scattering particles in a deadly wind. Another vanished into blackness, reflecting less light than charcoal. But the true marvel came when we began to understand what they might mean. That planets form not only in comfort, but in chaos. That they arise around stars old and new, rich and poor in metals. That they orbit pulsars and giants, dwarfs and dead remnants. That they can form anew from the ashes of supernovae. That where there is dust and time, there are worlds. The process is ancient. Dust becomes rock. Rock becomes planetesimal. Gravity draws them together. Heat sculpts them. Chemistry begins. It takes time, but not always as much as we thought. Around one of the oldest stars in our galaxy, TOI 561, we found a rocky world. The star is 10 billion years old. The planet must be nearly as ancient. Perhaps it had oceans. Perhaps it had life. Perhaps it still does. And what of life? We know only one world where life arose, but it did so quickly. It did so with stubbornness. If that pattern holds, then life too may be common. It may be old. It may be watching. Around a giant planet named Methuselah, orbiting within a globular cluster of stars, we found a world nearly 13 billion years in age. We do not know how it formed. We do not know if it lives, but we know it is ancient. And where there is age, there is time. And where there is time, there is possibility. The first planets may have known only fire and silence, but some endured. Some became cradles, and some, perhaps, became home. If life could survive the chaos of early galaxies, the fury of supernovae, the collapse of stars, then perhaps it is more common than we dared hope. We stand at the edge of that knowing. We send our eyes into space. We craft mirrors that will unfold in orbit, hunting for the signs we seek: water, oxygen, methane, disequilibrium. Not just the ingredients of life, but the breath of life itself. The telescopes to come will see further, sharper, deeper. They will not merely count planets. They will study them. They will reveal their atmospheres, their climates, their seasons. They will find, perhaps, the pale blue dots of other civilizations, or perhaps they will find the red deserts of a planet that tried and failed, or perhaps just silence. But even silence tells a story. It tells us where not to look. It tells us what paths not to follow. It narrows the possibilities. It sharpens our search. And so we continue, from the death throes of a nearby star to the icy memory of distant Arakoth, from the strangled orbit of a glowing Earth to the grandeur of ringed super Saturns. We chart a cosmos that teems with worlds. Many are harsh, some are beautiful, a few may be kind. But all of them matter. Each world is a chapter in a story that spans galaxies and epochs, and we, fragile and hopeful, are learning to read it. The skies are not empty. They never were. They are full of destinations, full of questions, full of homes, and maybe, just maybe, full of neighbors. In a star system 66 light-years from Earth, a small rocky planet orbits so tightly that it completes a full revolution in barely more than 2 days, scorched by its nearby sun and stretched by the violent gravitational tug-of-war of neighboring gas giants. This world glows like an ember. It is not volcanic. It is not molten. It is incandescent, lit not from within, but by the torment of tidal forces squeezing and twisting its rocky flesh. The heat generated from this ceaseless punishment pushes its surface temperature above 2000 Kelvin, igniting the very crust into radiance. From a distance, it might look like a slow-motion spark, drifting through a solar ballet that threatens to tear it apart. We have never seen its surface directly. We have never watched its glow, but its existence, its temperature, its tormented orbit, we know these from whispers in the light, from the slightest shifts in spectral lines, from dips in a star's brightness measured over months. It is extraordinary what we can learn from a single line on a graph. This planet is not alone. Thousands of such exoplanets crowd the expanding library of worlds, most known to us only as squiggles of light and shadow. But in those squiggles lies enough detail to paint rough portraits, to tell stories of fire and ice, of oceans lost and atmospheres born, of violence, silence, and survival. And behind these stories are spectrums, the coded light fingerprints of alien atmospheres, light filtered through distant air, tinged with the breath of exotic molecules. Astronomers work backward from these impressions. They take the physics of light, the chemistry of gases, the mathematics of planetary motion, and apply them like sculpting tools to shape the outlines of alien worlds. A hint of methane here suggests a reducing atmosphere. A dash of carbon dioxide there hints at volcanic activity. When water vapor appears, the signal is dim but electric with possibility. We do not need to visit these planets to begin understanding them. Some of the greatest surprises have come not from confirming what we expected, but from confronting what we never imagined. Take the hot Jupiters, gas giants, found orbiting so close to their stars that they ought not exist. These are worlds so close to their parent stars that their upper atmospheres puff outwards under the sheer assault of radiation, becoming distended, vulnerable to evaporation. In extreme cases, the atmosphere is so bloated that it forms a comet-like tail, dragged away from the planet in a constant hemorrhage of gas. The mystery of how such giants arrive at their unnatural proximity sparked decades of research. They could not have formed so near to their stars any nearby hydrogen, and helium would have long since evaporated in the early violent youth of stellar ignition. So they must have formed farther out and then migrated inward. A planetary journey that may have destroyed siblings, triggered collisions, or even changed the orbital layout of entire systems. These giant planets, once considered rare anomalies, are now a common feature of exoplanet catalogs. Their oddity helped make them easy to find. Their size and tight orbits yield strong signals. But as techniques improved, smaller worlds began to appear, worlds that might be rocky, that might cling to water, that might, in rare cases, nurture life. Around small red dwarf stars, the dim embers of the galaxy, many of these planets were discovered. These stars are faint, long-lived, and temperamental. Their planets, often tidally locked, face their star with eternal day on one side and endless night on the other. Still, many orbit in the so-called habitable zone, the region where liquid water might persist. Life, as we know it, depends on such water. And so the question becomes, can such worlds bridge that eternal twilight and give birth to something enduring? Of the methods astronomers use to find exoplanets, the transit technique reigns supreme. When a planet crosses in front of its star, even from our far-flung vantage, it causes a minute but measurable dip in light. The shape of that dip, the timing, the duration all tell us something. We can infer the planet's size, its orbital period, sometimes even the presence of clouds in its atmosphere. When combined with radial velocity measurements, which reveal how much a star wobbles due to the planet's gravitational tug, we can estimate a planet's mass. With both size and mass in hand, we get density, and from density, a guess stone or gas, iron or ice. Beyond Kepler, the transiting exoplanet, Survey Satellite, or TESS, has taken up the mantle. It scans swaths of sky, hunting for those subtle flickers. Thousands of candidate worlds have emerged from its gaze, some confirmed, many still waiting. Among them is a world nicknamed Phoenix, orbiting a star so massive it should have boiled the planet dry. Yet Phoenix retains an atmosphere, hugging it close like a secret. For now, models suggest it may be living on borrowed time. And soon, the next generation will arrive. The Nancy Grace Roman Space Telescope, launching in the near future, will use microlensing, a technique that relies on gravity itself to reveal planets. When a star passes in front of another star, the gravity of the foreground star can bend and focus the background light. And if a planet happens to be orbiting the foreground star, its presence can leave a detectable fingerprint in the light. This method is unbiased toward size or orbit, opening a window to a vast new population of hidden worlds. But even beyond finding planets, we aim to know them, to read their air, to see their surfaces. The James Webb Space Telescope has already begun this work. With its infrared gaze, it has peered into the clouds of gas giants, read the atmospheres of sub-Neptunes, and caught the faint exhalations of worlds dozens of light years away. Methane, carbon dioxide, water vapor, all have been spotted. In the spectrum of K2-18b, an intriguing mix of chemicals emerges, whispering of processes that, on Earth, would require life. None of this guarantees that life exists there. Abiotic chemistry can mimic biology in deceptive ways, but what matters is not certainty, it is possibility. For every such planet we detect, for every hint of habitability, the stage widens. The play becomes grander. The universe becomes a canvas that might include life again and again in endless variations. We live in an age where light alone tells us of distant worlds. We listen for silence and find symphonies. We peer into the dark and find it filled with echoes. Somewhere out there, beneath thick clouds or icy crusts, the conditions that cradle life may have arisen. And in knowing that, we begin to prepare, not just to discover more, but to ask deeper questions. What makes a world alive? What keeps it breathing? And how many candles has the universe lit, only to let them burn unseen? The cosmos is not silent. It speaks in spectra, pulses, and gravities. And with every passing year, we learn a few more syllables of its language. Among the stars, the stories of planets continue to unfold, stories of agony, survival, migration, and balance, each one a chapter in a cosmic novel still being written, and somewhere in those stories may lie the preface to our own. Somewhere in the galactic heart of a spiral arm, a new world begins to take shape. A star is born from a collapse of dust and gas, its ignition the signal for a planet-forming dance to begin. Around this star, a disk flattens and spins, littered with the debris of creation. Within this chaotic swirl, dust clings to dust, grains coalesce, and the earliest seeds of planets take root. This is how it has always begun. And across the galaxy, it is happening again and again. We know this not from direct observation, but from scattered glimpses. We have seen stars still wrapped in their disks, illuminated from within by fusion barely begun. We have seen young systems with arcs and gaps carved by infant planets. These fleeting moments, like frames in a cosmic film reel, are all we need to stitch together the tale of planetary birth. The process unfolds slowly by human standards, but swiftly on cosmic scales. Within a few million years, what was once dust becomes a planetesimal. Within tens of millions, these grow into full-fledged worlds. The location within the protoplanetary disk matters. Close to the star, the heat drives away volatiles, leaving behind iron and rock. Farther out, beyond the snow line, ice and gas can accumulate. Here, giants are born, and between these two extremes lies the fertile band we call the habitable zone. But this is not a static range. Stars evolve, orbits shift. What is temperate today may be seared tomorrow. And yet, despite all this, the universe seems insistent on building planets. Even in environments we once thought hostile to their formation, planets appear around old, metal-poor stars like Teofard 61, around binary systems, around the remnants of supernovae. Even around the cosmic undead pulsars and white dwarfs worlds have been found. This resilience suggests that once the universe had the raw materials, planets became inevitable. Stars light the stage, but planets are the actors, and some of those actors may carry life. What we have begun to understand, slowly and with caution, is that diversity is the law of exoplanets. For every Earth-like world we seek, a dozen others surprise us, some with compositions beyond prediction, others with orbits that defy classical mechanics. Take the circumbinary planets, orbiting two suns in a delicate, synchronized ellipse, or rogue planets, flung from their systems to wander lightless and alone. These drifters, cold and forgotten, may yet retain internal heat, with a thick enough blanket of atmosphere or an insulating ocean beneath an icy shell. Even these could harbor microbial life. Planetary mass, orbit, and composition are not the only keys. Time is a factor. Planets need time to cool, time to stabilize, time to host chemistry. Around stars that live for billions of years, time is abundant. Red dwarfs, for all their flaring rage, offer longevity. Some will burn for 100 billion years or more, long after the sun has expired. Their planets, if they survive the early tantrums of youth, may be the longest-standing homes for life in the universe. And then there are the atmospheres, thin or thick, scorching or frigid, transparent or opaque. Atmospheres reveal as much as they obscure. They are both veil and window. In them, we search for biosignatures, chemical imbalances that, on Earth, would suggest biology. Oxygen paired with methane, carbon dioxide alongside water vapor. These are fragile combinations. On Earth, they persist only because life continually replenishes them. If we find them elsewhere, we cannot assume life, but we cannot ignore the hint. Already, James Webb has turned its eye to promising targets. K2-18b stands out a world, neither Earth nor Neptune, wrapped in a dense atmosphere, showing whispers of methane and carbon-bearing compounds. It is a candidate, not a confirmation, but even one candidate is cause for hope. We are now at the threshold where planets are not only known, but characterized. This transition marks a new era. The age of exoplanet discovery is becoming the age of exoplanet exploration. And with the upcoming Habitable Worlds Observatory, we hope to go further, to photograph a pale dot orbiting a sun-like star, to separate its light, to read its air, to see if it breathes. This telescope, still on the drawing board, will unfold in orbit like a mechanical flower. Its mirrors will be vast, its vision sharp enough to find the fingerprints of life across the void. But such ambitions demand patience. The design, testing, construction, and launch span decades. The data, once it arrives, must be parsed carefully, compared, modeled, and retested. False positives abound. Confirmation is slow, yet there is no rush. The universe is old. The planets have waited. And while we wait, we imagine, we model molten exoplanets, oceans of lava under skies of silicate rain. We simulate super-Earths with crushing gravity and air like syrup. We dream of water worlds with no land at all, just endless sea under clouds that never break. We speculate about diamond planets, forged in high-pressure crucibles. Each possibility is a thought experiment, a boundary pushed. This is the scientific imagination at its best, grounded in data, but unafraid to dream. And every new telescope, every new detection, turns dream into question, and question into experiment. What we imagined yesterday, we might observe tomorrow. So much of what we now accept as common gas giants in tight orbits, planets around red dwarfs, moons with subsurface oceans, was once thought improbable or impossible. The lesson is clear: expect surprise. The universe is under no obligation to conform to our intuition. And so we return to the skies, to the data, to the spectra, to the equations. Each planet is a story, and every story begins with a few points of light. With time, those points become portraits, and some portraits begin to smile back. The stars do not hide their children. We have only just learned how to look. The first light in the universe did not come from planets. It did not come from life. It emerged from the collapse of primordial hydrogen, from the ignition of the first stars in a cosmos, barely a few 100 million years old. These stars were immense. short-lived titans that lived fast and died violently, spewing heavy elements into their surroundings. In death, they gave the cosmos the ingredients it needed to begin building the second generation of stars and, eventually, the first planets. From that ancient starlight came the foundations for all worlds. The dust scattered by early supernovae seeded the galaxies with carbon, silicon, oxygen, and iron, the scaffolding of rock and metal. Yet those elements were sparse, and the early universe remained hostile. Frequent collisions between forming galaxies, bursts of radiation from quasars and gamma-ray bursts, and the chaotic dance of gravitational interactions made it a turbulent cradle. And still, the universe persisted. Planets formed, moons accreted, gas giants migrated, and some small rocky worlds settled into orbits just right for warmth and water. The first truly ancient planets likely formed when the universe was less than 1 billion years old. These were not necessarily Earth-like, but they were solid, real places, perhaps scorched, perhaps frozen, perhaps gaseous. They orbited metal-poor stars that had nonetheless acquired just enough building blocks to birth something more than light. Some of these worlds may have endured for billions of years. Some may still circle their ancient suns, quiet and unchanged, since a time before galaxies had even settled into their modern spirals. Among these elders is Methuselah, a gas giant orbiting a pulsar in the globular cluster M4. It is over 12 billion years old. Its origin story is tangled, formed around a sun-like star, captured by a neutron star, its system reshaped by stellar collisions and gravitational entanglements. Methuselah is a survivor, and if it formed moons in its youth, some of them may have harbored oceans beneath thick ice. Sheltered from radiation, they could have given life a fighting chance when the rest of the galaxy was still an inferno. But life, if it ever arose there, has remained hidden. No signal has reached us from those depths. No probe has passed by. We know of Methuselah only because its timing whispers through space. The pulsar it orbits ticks like a cosmic metronome, and the planet's presence perturbs the beat. From such delicate rhythms, we read the presence of a world that has seen almost the entire history of time. The strange thing is, the universe does not seem selective in its generosity. It makes planets easily, almost frivolously. It scatters them across billions of stars, forms them even around the corpses of stars, and lets them drift alone through interstellar space. There are rogue planets without suns, planets that formed and were flung away by violent reshufflings. These cold, sunless worlds may number in the billions within our galaxy alone. Some may retain heat for eons. Some may have thick atmospheres, or oceans buried beneath frozen shells, warmed by radioactive decay. There is even a class of planets that may not orbit any star but glow faintly with heat from their formation, visible only to the most sensitive infrared instruments. These planetary ghosts haunt the void between stars, unmoored from any system, relics of instability. Their darkness hides their secrets. We know they exist. We do not yet know how many. And the universe continues to build. With every passing million years, new stars ignite, new disks form, new planets accrete. The current age of planet formation is not over. It is ongoing, especially in the spiral arms of galaxies like our own. And as each new planetary system emerges, the potential for life flickers anew. If life arises easily, it could be blooming on 1,000,000 worlds this very moment. If it is rare, those first worlds might still be the only cradles it has ever known. We cannot yet say. The data is too sparse, the distances too great, the signals too faint. But the search sharpens. Missions are planned, telescopes built, algorithms refined. The Habitable Worlds Observatory will one day look at exoplanets, not as abstract data points, but as places we can image, study, and dream about. We will analyze their skies for disequilibrium, the chemical fingerprints that suggest life interfering with chemistry, oxygen, methane, ozone, nitrous oxide. Any one of these might be produced by non-biological processes, but find them all together, in the right balance, and the case becomes stronger. If we find such a world, the implications are staggering. It would mean that life is not confined to Earth, that biology is not a cosmic fluke, that the universe is not silent, but singing life into being wherever conditions permit. It would not answer all our questions, but it would break the loneliness. It would change our story. And if we do not find such signals, if the skies of all surveyed planets remain quiet, their spectra unbroken by the telltale signs of breath and metabolism, then the mystery deepens. It could mean that life is truly rare, that intelligence is rarer still, that Earth is an anomaly. Or it could mean we are still early in our search, still unpracticed in interpreting the whispers of alien atmospheres. What we do know is that planets come easily, life, perhaps less so, civilization, rarer yet. And so each discovery pushes us to reflect not just on the cosmos, but on ourselves. If there are billions of planets, and we are alone among them, what responsibility does that confer? If we are not alone, how do we choose to meet that future? The universe is old. The stars burn with memories. Some planets may have watched galaxies collide, watched quasars blaze, watched the spiral arms of the Milky Way twist and reform. And if any life watched from those planets, it too witnessed a universe in motion, in drama, in ceaseless change. From the fire of early stars to the cold tranquility of rogue worlds, from gas giants wrapped in storms to rocky moons with oceans beneath their shells, the variety is staggering. Yet in that variety lies a kind of unity. The same laws of physics shape every world. The same elements combine in endless patterns. The same gravity binds every orbit. The cosmos is not chaotic. It is intricate. And so we listen, with radio waves, with infrared telescopes, with gravitational microlensing, with our models, our theories, and our hope. We listen to the stories planets tell, stories that began long before we were here, stories that may continue long after we are gone. For every world out there, there is a question. Did life begin? Did it last? Did it speak? And for every answer we find, we take one step closer to understanding our place in the vastness. Perhaps we are the cosmos becoming aware of itself. Perhaps we are just a flicker in the dark. But we are a flicker that looks outward. And in that looking, we become part of the story.
What if humanity were to transcend its current limitations, leaving behind the confines of Earth to inhabit the vast expanse of space? What if, after countless millennia of expansion, our descendants filled the Milky Way constructing a civilization that stretched from the galactic core to the most distant spiral arms. And what if, one day, a message arrived from another galaxy, an unmistakable sign that we were not alone? The prospect of first contact with an alien intelligence is one of the most profound questions in modern science. Through communication, the exchange of knowledge would flourish, advancing science, philosophy, and technology in ways previously unimaginable. And ultimately, a historic meeting would be planned, an encounter between two great civilizations in the dark void of intergalactic space. Generations would toil to construct immense vessels capable of bridging the cosmic gulf. Generations would be born, live, and die as these titanic ships traveled the void. And then, after eons of anticipation, the moment would arrive. Two emissaries, one from each civilization, floating toward each other, reaching out across the abyss. But in an instant, catastrophe unfolds. The moment of contact results in an explosion of unimaginable energy. The great ships stand off in stunned silence, their crews now understanding a tragic truth. One civilization is composed of matter, the other of antimatter. Physical contact means mutual annihilation. How could this have happened? How could two advanced species, having shared their knowledge of mathematics, physics, and engineering, have overlooked such a fundamental difference? The answer lies in the subtlety of the universe's design. Nature, as always, holds its deepest truths in concealment, governed by rules that defy easy discovery. Throughout the cosmos, asymmetry is fundamental. The laws that govern reality were set in motion within the first billionth of a second after the Big Bang. From the quantum level to the largest structures in the universe, these principles dictated how matter and antimatter evolved, ensuring that they remained separate. While mathematical equations predicted the existence of both, the true nature of their division remained obscured. In the end, this paradox highlights the limitations of knowledge. Even as civilizations strive toward understanding, the fundamental nature of the cosmos enforces constraints that shape reality in ways both profound and inescapable. And behind all of these mysteries, behind the vast complexity of existence, there is always one common factor: the immutable laws of the universe itself. Symmetry is everywhere. Two civilizations, separated by vast cosmic distances, bound by the same fundamental laws of physics, yet doomed by their inability to perceive a crucial difference. How could they have failed to recognize the distinction between matter and antimatter? How could two particles, two atoms, two intelligent beings from opposite ends of the universe, carrying opposite electric charges, remain unaware of their incompatibility? In our observable universe, matter dominates, while antimatter is scarce. But if the cosmos is truly vast and diverse, it stands to reason that somewhere, the inverse must be true, a region where antimatter is the norm, where stars and planets are composed of antiatoms, where life flourishes in forms opposite to our own. It would seem intuitive to assume that the laws of physics are indifferent to this distinction, that nature treats matter and antimatter with perfect symmetry. But this is not entirely correct. We now know that, while nature is built upon symmetrical principles, it also introduces subtle asymmetries, differences so minute yet so consequential that they govern the very fabric of the universe. And at the heart of this lies one of the most profound concepts in physics: symmetry. Our first encounter with symmetry is often visual, an image reflected in a mirror, the left mirroring the right. A child can instinctively sketch symmetrical shapes by drawing one side and copying its reflection. This bilateral symmetry is deeply embedded in nature, our bodies, with matching left and right sides, the mirrored structure of mammals, birds, and fish. When nature occasionally breaks the symmetry, as with the enlarged claw of a fiddler crab, the effect is striking. But symmetry extends far beyond simple reflection. A starfish exhibits rotational symmetry. It appears the same when rotated by certain angles. A millipede employs translational symmetry, constructing its body from repeating segments. These patterns reveal nature's tendency toward efficiency, using symmetry to streamline development and function. Symmetry is also deeply embedded in human culture. It influences our perception of beauty, architecture, and art. From the temples of ancient Egypt and Greece to the geometric precision of the Taj Mahal and the Arc de Triomphe, symmetry conveys harmony and order. Artists and architects have long recognized the power of symmetry, utilizing both reflectional and rotational forms, from Da Vinci's compositions to the intricate designs adorning Islamic mosques. Even modern structures like the Pentagon, where there's symmetry as a defining feature. But how does symmetry relate to the fundamental laws of the universe? To answer that, we must journey back to a fateful morning in 1832 when two men met in a field outside Paris. The cause of their duel is uncertain. Some say it was over the affections of a woman, but by sunrise, 20-year-old mathematician Évariste Galois lay dying in the grass. The night before his death, Galois, sensing his fate, spent his final hours writing letters and feverishly documenting his mathematical ideas. Unbeknownst to him, these writings would transform the future of mathematics, introducing a revolutionary approach to understanding symmetry. The study of symmetry was not new. Ancient geometers had observed that a circle remains unchanged when rotated, and that triangles and squares maintain symmetry under fixed transformations. But Galois delved deeper. His interest lay in algebra, particularly in the structure of polynomial equations. Polynomials, equations with variables raised to various powers, are ubiquitous across mathematics and science. For centuries, mathematicians sought a general formula to solve higher-order polynomial equations, but Galois approached the problem differently. Instead of attempting to construct solutions, he examined the underlying symmetries of the equations themselves. He realized that the solutions to polynomial equations could be visualized as points in a complex plane, forming geometric shapes, triangles, pentagons, and beyond. These shapes, like physical objects, exhibited symmetries. They could be rotated or reflected while preserving their fundamental properties. By analyzing these symmetries, Galois revealed a profound truth. There exist certain polynomial equations for which no algebraic solution can ever be found. His discovery gave birth to what we now call group theory, the mathematical study of symmetries. Since Galois' time, group theory has expanded beyond pure mathematics, permeating physics, chemistry, and even cryptography. In physics, symmetries govern fundamental interactions, dictating the behavior of particles and forces. The standard model of particle physics, our best description of the subatomic world, is built upon group theory. Even the asymmetry that distinguishes matter from antimatter, an anomaly that shaped the fate of our universe, finds its explanation in the subtle breaking of fundamental symmetries. As he lay dying, Galois could not have foreseen the vast impact of his final scribbles. Yet, his insights now underpin the laws that describe our universe, from the tiniest particles to the grandest cosmic structures. Symmetry, once a simple aesthetic principle, has revealed itself as one of the deepest, most fundamental truths of reality. Long before physical contact was established, two great civilizations, separated by unimaginable distances, found a way to communicate. Streams of electromagnetic waves, fired from one world to another, traversed the void over millions of years before reaching their destinations. The process was slow, limited by the fundamental constraints of light-speed communication, yet it worked. The shared knowledge of electromagnetism allowed two alien species to converse across the abyss of space. On Earth, the messages were encoded within the rhythmic oscillations of electrons, forming coherent radio signals. But on the other end, across the cosmic gulf, the same process occurred with a subtle difference. Positrons, the antimatter counterpart to electrons, responded to the signals instead. The laws of electromagnetism possess a profound symmetry. If one were to swap all positive and negative charges, the equations governing their behavior would remain unchanged. The dance of electrons on one world mirrored the dance of positrons on another. And therein lay a fundamental problem. Electromagnetic waves alone could not distinguish matter from antimatter. The universe had to possess some deeper asymmetry, some hidden rule that could reveal the nature of reality. To understand this, we must journey back nearly a century to the work of one of the most brilliant minds in mathematical physics, whose insights unlocked the deep symmetries that shape our universe. On May 1st, 1935, an obituary appeared in the New York Times, penned by none other than Albert Einstein himself. It commemorated the passing of Emmy Noether, a name far less renowned than Einstein's, but whose contributions to physics were no less profound. Einstein described her as the most significant creative mathematical genius thus far produced, and credited her insights with deepening our understanding of the natural world. Despite her extraordinary intellect, Emmy Noether's name remains unfamiliar to many outside of physics. Yet her theorem, a statement about symmetry and conservation laws, lies at the very foundation of modern physics, from classical mechanics to quantum field theory. To grasp its significance, we must first understand a fundamental truth about the universe. It is inherently lazy. Throughout history, mathematical principles have gradually supplanted mysticism, revealing the underlying structure of reality. The symmetries of nature became evident as our equations grew more refined. Newton's gravity produced the near-perfect spheres of planets and stars, while Maxwell's equations dictated that electric currents generate cylindrical magnetic fields. But beneath these familiar geometric symmetries lay deeper, more abstract symmetries, ones governing the very laws of motion and energy. Two mathematicians, separated by a century, played key roles in uncovering these hidden truths. The first, Giuseppe Lodovico Lagrangia, better known as Joseph Louis Lagrange, lived through the turbulence of the French Revolution and was instrumental in standardizing the metric system. The second, Irish mathematician William Rowan Hamilton, was a prodigy who reshaped our understanding of mechanics. Their work converged on a radical reformulation of Newtonian physics, rooted in a single, elegant idea, the principle of least action. The essence of this principle is deceptively simple. Nature always takes the most efficient path. Light, for example, travels between 2 points in the least possible time, bending at the interface between air and water much like a lifeguard racing to save a drowning swimmer, moving quickly on land before entering the slower medium of water at an optimized angle. This insight, first proposed by Pierre de Fermat in optics, was expanded by Lagrange and Hamilton to encompass all of physics. They discovered that every physical system, from the motion of planets to the behavior of subatomic particles, follows a path that minimizes a quantity called action. The reasons for this universal tendency toward efficiency remain mysterious, but its predictive power is undeniable. Physicists define action mathematically and consider all conceivable paths a system could take. Among these infinite possibilities, nature always selects the path that minimizes action. This principle governs everything, from Newton's mechanics and Maxwell's electromagnetism to quantum mechanics and Einstein's general relativity. It is a law not of force, but of optimization. And it was within this mathematical framework that Emmy Noether discovered something remarkable. While investigating the mathematical structure of physical laws, Noether noticed a profound connection between symmetry and conservation. She demonstrated that whenever a system possesses a symmetry, there exists an associated conserved quantity. This revelation, now known as Noether's theorem, has since become one of the cornerstones of theoretical physics. The most intuitive example is the conservation of energy. The laws of physics remain unchanged whether an experiment is conducted today or tomorrow, as symmetry in time. Noether's theorem reveals that this time invariance leads directly to energy conservation. Similarly, spatial symmetry, the idea that the laws of physics do not change if an experiment is moved 10 meters to the left, gives rise to the conservation of linear momentum. And rotational symmetry, the principle that physics is the same regardless of the direction one faces, ensures the conservation of angular momentum. These conserved quantities govern everything from planetary orbits to atomic interactions. Yet the implications of Noether's theorem extend far beyond classical physics. In the quantum realm, Symmetries dictate the very existence of fundamental forces and particles. At the heart of quantum mechanics lies the wave function, a mathematical description of a particle's state. These wave functions possess their own symmetries, which in turn correspond to conserved quantities. The symmetry of an electron's wave function under phase shifts, for example, leads directly to the conservation of electric charge. In the realm of particle physics, even more exotic symmetries emerge. These include conservation laws for baryon number, lepton number, and quantum numbers such as isospin and strangeness. Gauge symmetries, underlying principles in quantum field theory, predict the existence of fundamental force carriers like gluons, which bind protons and neutrons together, and the W and Z bosons, which mediate the weak nuclear force. Physicists at the Large Hadron Collider probe these conservation laws, studying the minute violations and anomalies that hint at new physics. For while the universe is governed by symmetry, it is in the rare breaks in symmetry that some of the greatest mysteries lie. Despite the power of Noether's theorem and the principle of least action, there exist subtle asymmetries in nature. One of the greatest of these is the imbalance between matter and antimatter. If the laws of physics were perfectly symmetrical, the Big Bang should have produced equal amounts of both, leading to a universe where matter and antimatter annihilate, leaving nothing behind but pure energy. Yet the observable universe is overwhelmingly composed of matter. Somewhere, deep within the laws of physics, a fundamental asymmetry tipped the balance, allowing matter to dominate. Understanding this asymmetry remains one of the greatest challenges in modern physics. But one thing is clear: while symmetry governs the universe, it is in its subtle imperfections that the very fabric of reality was shaped. In the grand cosmic dialogue between distant civilizations, symmetry and conservation laws define the rules of communication. But hidden within those laws, in the tiny cracks where symmetry breaks, lies the key to existence itself. As we continue to probe the universe's deepest mysteries, we stand on the shoulders of giants: Einstein, Lagrange, Hamilton, and Noether, who revealed the mathematical elegance of a universe that, though governed by symmetry, was shaped by its exceptions. How to break the universe? By the mid-20th century, the possibility of extraterrestrial intelligence was no longer a mere speculation of science fiction. Astronomers, armed with powerful radio telescopes, began scanning the cosmos for any faint signals, an encoded message, a structured pulse, anything that might indicate the existence of intelligent life beyond Earth. The prospect of interstellar communication raised profound questions. What should we say? How could we construct a universal message that any advanced civilization, regardless of biology or culture, could understand? But a deeper, more unsettling problem lurked beneath these considerations: the problem of parity and the distinction between matter and antimatter. If we ever made contact with an alien race, how would we explain the difference between left and right? More than a trivial exercise in orientation, this question bore a direct connection to the underlying symmetries of physics and the fate of the universe itself. To communicate left and right across the void of space, we would need to appeal to a fundamental break in the symmetries of nature. And that is where the story of parity begins. The concept of parity, or mirror symmetry, had long been assumed to be a fundamental property of the universe. In classical physics, the laws governing the motion of objects remain unchanged if one swaps left with right, just as a reflection in a mirror is indistinguishable from the original scene. Even in quantum mechanics, parity was believed to be preserved in fundamental interactions. That assumption was shattered in 1956 when physicist Qian Wu conducted a groundbreaking experiment on the weak nuclear force. In her laboratory in Washington, D.C., she cooled cobalt-60 atoms to near absolute zero and aligned them in a magnetic field. These atoms were radioactive, meaning they decayed over time, emitting electrons as they transformed into different elements. If parity were truly conserved, the emitted electrons should have been expelled symmetrically, equal numbers moving in opposite directions along the axis of spin. Yet, to the astonishment of Wu and the physics community, the electrons did not behave as expected. Instead of an even distribution, they overwhelmingly emerged from only one side of the cobalt atoms. The universe, it seemed, had a preference. It was not perfectly symmetrical. To understand the implications of Wu's experiment, one must first examine the fundamental forces of nature. In the realm of particle physics, four fundamental interactions govern the behavior of matter: electromagnetism, the force that binds atoms and governs the interaction of charged particles, strictly conserving parity; gravity, the curvature of space-time caused by mass, also respecting mirror symmetry; the strong nuclear force, the force that holds protons and neutrons together in atomic nuclei, obeying all known symmetries; the weak nuclear force, the force responsible for certain types of radioactive decay, which, as Wu's experiment revealed, violates parity. For decades, physicists had assumed that all fundamental forces treated left and right as interchangeable. But Wu's results forced a paradigm shift. The weak interaction, unlike all other forces, inherently distinguishes between left and right. This meant that an alien civilization, regardless of its technological advancement, could determine which way was left and which way was right, simply by studying the weak nuclear force. The weak interaction's asymmetry suggested that certain particles might only exist in one handedness. Enter the neutrino, a ghostly particle predicted by Wolfgang Pauli and required to preserve the conservation of energy in radioactive decays. Though nearly massless and interacting only through the weak force, neutrinos play a crucial role in the universe's underlying symmetry structure. Wu's experiment hinted at a deeper truth about neutrinos. They always spin in one particular direction relative to their motion. Unlike all other known particles, neutrinos are never observed to spin the other way. If you were to place a neutrino in front of a mirror, its mirrored counterpart could not exist in our universe. Nature, at its most fundamental level, had a preferred handedness. This discovery was so shocking that it led to the 1957 Nobel Prize in Physics for Chen-Ning Yang and Tsung-Dao Lee, the theorists who first proposed testing parity violation. Curiously, Wu, despite conducting the experiment that confirmed their theory, was overlooked. While parity violation was already a groundbreaking revelation, another puzzle soon emerged: the possible violation of CP symmetry, the combined symmetry of charge and parity. If parity alone was not conserved, perhaps nature still obeyed a deeper rule, one that combined the mirror reflection with the exchange of matter and antimatter. In 1964, James Cronin and Val Fitch designed an experiment using neutral kaons, particles composed of a quark and an antiquark. Their decays were expected to obey CP symmetry, meaning that if one switched both charge and parity, the physics should remain unchanged. Yet, once again, nature defied expectations. Kaons occasionally decayed in a way that violated CP symmetry. This was not just an abstract peculiarity of particle physics. It had profound consequences for the entire universe. The violation of CP symmetry hinted at a possible explanation for one of the greatest mysteries of cosmology, the matter-antimatter asymmetry. If matter and antimatter had been created in equal amounts during the Big Bang, they should have annihilated each other entirely, leaving behind only radiation. And yet, the observable universe is overwhelmingly composed of matter. CP violation provided a potential escape from this paradox. If the laws of physics slightly favored matter over antimatter in the early universe, even by the smallest fraction, that imbalance could have led to the cosmos we see today. The neutral kaons in Cronin and Fitch's experiment, decaying in a slightly biased way, were a tiny echo of this grand cosmic asymmetry. The violation of parity and CP symmetry reshaped our understanding of fundamental physics. It revealed that the universe is not perfectly balanced, that nature has preferences, and that the rules governing matter and antimatter are not as symmetric as once believed. The implications extend beyond theoretical physics. They touch the very reason we exist. If the weak force had been perfectly symmetrical, if CP violation had not occurred, then the universe might have been a lifeless expanse of radiation, devoid of galaxies, stars, and planets. The universe, as it turns out, is broken, but in that imperfection lies the reason for our existence. Why did the universe freeze? What is the ultimate goal of fundamental physics? Is it to decipher the nature of reality, to uncover the origins of the universe? To Einstein, even in his final days, the answer was clear. The ultimate prize was a theory of everything, a framework that would unite all fundamental forces into a single, elegant equation. These forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, govern the fabric of reality. For more than a century, physicists have worked to unify them, making steady progress. In the 1960s, the weak nuclear force was successfully unified with electromagnetism under the electroweak theory. Later, the strong nuclear force found its place within quantum chromodynamics. But one force has remained elusive: gravity. The incorporation of gravity into a unified theory remains the final frontier, the missing piece of a puzzle that has captivated physicists for generations. How do physicists build such theories? The guiding principles are symmetry and perfection, two concepts that lie at the heart of nature's design. And to unravel the history of these forces, we must journey back to the beginning of time itself. In the extreme conditions of the early universe, matter and energy existed in an almost unimaginable state. As physicists have uncovered, at sufficiently high energies, the fundamental forces of nature begin to lose their individuality. Their distinct properties fade, and they merge into a single, unified force. Consider electromagnetism and the weak nuclear force. In today's universe, they appear radically different. Electromagnetism governs electric and magnetic interactions, while the weak force is responsible for certain forms of radioactivity. Their mediators, the photon and the W and Z bosons, have vastly different properties. Yet, at sufficiently high temperatures, they become indistinguishable. This is the foundation of the electroweak theory, which tells us that in the early universe, only a single electroweak force existed. It was only as the universe cooled that symmetry was broken and the two forces became distinct. The same principle applies at even higher temperatures. This strong nuclear force, which binds quarks into protons and neutrons, is fundamentally different from electromagnetism and the weak force in today's universe. But at extreme energies, these differences vanish, hinting that all three forces, strong, weak, and electromagnetic, were once one. And beyond that, theoretical physics suggests that gravity, too, may have been part of this unification. If so, the very birth of the universe was a time of perfect symmetry, when a single superforce ruled all. In the opening moments of the universe's existence, everything was unified. But as the cosmos expanded and cooled, the symmetry of the superforce fractured. One by one, the fundamental forces split off, altering the very nature of the universe at each stage. This process can be understood through the concept of phase transitions, the same principle that governs the transformation of liquid water into solid ice. Just as water loses its liquid symmetry when it freezes, the forces of nature lost their unity as the universe cooled. The first major transition came when gravity separated, an event that likely occurred at the Planck time, around 10 superscript 3 seconds after the Big Bang. This era remains a mystery, shrouded in the unknown physics of quantum gravity. Without a complete theory uniting quantum mechanics and general relativity, the precise nature of this transition remains speculative. The next major fracture came at around 10 superscript 3 seconds, an epoch when the strong nuclear force separated from the electroweak force. This is an era physicists believe they understand much better. It was around this time that the universe underwent one of its most dramatic and transformative events, cosmic inflation. In the late 1970s, physicist Alan Guth confronted an unsettling question about the early universe. Why did the cosmos appear so perfectly flat? Why was it not curved like a sphere or shaped like a saddle? Guth realized that the universe must have undergone an incredible expansion, a period during which space itself stretched exponentially. But Goose's work was also inspired by another mystery, the absence of magnetic monopoles. James Clerk Maxwell's equations of electromagnetism implied the possible existence of isolated north or south magnetic poles, yet none had ever been observed. Symmetry suggested they should exist, but they were nowhere to be found. Goose proposed that magnetic monopoles had once been common in the early universe, but were diluted beyond detection by the rapid expansion of space. This idea led to his revolutionary proposal, inflation. During inflation, the universe expanded exponentially, doubling in size 80 times in an instant. This immense stretching smoothed out the geometry of space, explaining its observed flatness, and diluted any exotic particles, like magnetic monopoles, beyond detectability. After inflation, the universe settled into a more conventional expansion, but by then, the fundamental forces had permanently split. As a result, the universe we observe today is a relic of that transformation, frozen in its current form, shaped by the breaking of once perfect symmetries. The breaking of cosmic symmetry was not just an academic curiosity, it was a defining moment in shaping reality. If inflation had not occurred, if the forces of nature had not separated, the universe as we know it would not exist. The intricate structures of galaxies, stars, and planets all trace their origins to these primordial fractures in symmetry. And yet, mysteries remain. The final unification of gravity with the other forces continues to elude physicists. The universe's fate, whether it will expand forever, collapse in a big crunch, or transition into another phase, depends on the deepest laws of nature, many of which remain undiscovered. But one thing is clear. In the beginning, there was unity. A perfect, symmetrical force ruled the cosmos. And then, as the universe cooled, perfection gave way to imperfection. The laws of physics as we know them emerged from that breaking of symmetry. The universe, once fluid and formless, froze into its present state. And in that frozen cosmos, we exist, products of a broken, yet beautifully structured, reality. In the earliest moments of the universe, an enigmatic field known as the inflaton dominated the cosmic landscape. The energy density of the universe plummeted dramatically as particles were stripped of their energy, leaving behind an eerily empty and frozen expanse. Yet, beneath this apparent stillness, space itself remained in turmoil. Eventually, the inflaton decayed, marking the end of cosmic inflation and reintroducing its vast reserves of energy back into the universe. This process, known as reheating, elevated the temperature of the cosmos to unfathomable extremes, billions of degrees, giving rise to the primordial matter from which everything we observe today has evolved. However, a curious absence became apparent: the elusive magnetic monopoles, predicted by grand unified theories, were nowhere to be found. Intriguingly, the onset of this inflationary epoch coincided with a crucial phase transition, the moment when the strong nuclear force separated from the other fundamental interactions. Was this synchronicity a mere coincidence, or was the very act of symmetry breaking responsible for energizing the inflaton field? The details remain uncertain, as our understanding of physics at such extreme conditions remains incomplete. While some theorists posit a connection between the inflaton and the emergence of the Higgs field, the very field responsible for endowing particles with mass, others speculate that the inflaton may represent an early manifestation of what we now refer to as dark energy. By the time the universe had aged to a mere 10 superscript 1 superscript 2 seconds and reached a scorching temperature of 10 superscript 1 K, the fundamental forces had fully separated into the distinct interactions we recognize today. Yet, the process of symmetry breaking had yet another profound consequence: the emergence of baryogenesis. During this critical period, the primordial sea of quarks and gluons began to condense into protons and neutrons, giving birth to the matter that forms the foundation of our universe, including the very atoms composing us. However, this transformation was accompanied by an enduring mystery: the observed asymmetry between matter and antimatter. The energy liberated by the inflaton during reheating should have produced equal amounts of matter and antimatter. Yet, observations reveal a stark imbalance. Across the cosmos, matter overwhelmingly dominates, with only minuscule traces of antimatter detected. Within our Milky Way, for instance, estimates suggest that for every quadrillion particles of matter, only a single particle of antimatter exists. The origin of this asymmetry is thought to lie within baryogenesis itself. While modern physics acknowledges subtle differences in the behavior of matter and antimatter, such as CP violation, the known effects are insufficient to account for the vast excess of matter we observe. Thus, the precise mechanism that tipped the balance remains one of the most profound unsolved mysteries in cosmology. The cosmic microwave background, the afterglow of the universe's early epochs, provides an indirect measure of this asymmetry. The sheer abundance of these photons relative to protons and neutrons, approximately 1 billion to 1, implies that the universe was nearly symmetric at its inception. A mere 1 in a billion imbalance in favor of matter over antimatter led to the existence of all the structures we see today: galaxies, stars, planets, and life itself. This realization is humbling. The very fabric of our existence hinges on a seemingly insignificant statistical deviation. Without it, the annihilation of matter and antimatter would have left behind a universe devoid of structure, an empty void of radiation. Yet, symmetry's role in shaping the cosmos does not end there. If the fundamental principles of physics are truly symmetrical, then our universe should harbor more than just hypothetical magnetic monopoles. A more profound symmetry, supersymmetry, suggests the existence of an entire hidden sector of particles. Each known particle in the standard model would have a supersymmetric counterpart: squarks for quarks, selectrons for electrons, neutrinos for neutrinos, and so forth. These hypothetical sparticles are an integral feature of many proposed grand unified theories and string theories, offering potential solutions to lingering questions about dark matter and the unification of forces. Yet, despite rigorous searches, the Large Hadron Collider has yet to reveal direct evidence of these supersymmetric partners. Some physicists argue that symmetry has misled us and that alternative frameworks must be considered. Others remain steadfast, convinced that the elegance of supersymmetry is too compelling to abandon prematurely. The search continues. As we approach the conclusion of this journey, one thing becomes clear: symmetry is a cornerstone of our understanding of the universe. However, it is the breaking of symmetries that has imbued the cosmos with structure, diversity, and complexity. From the formation of fundamental forces to the emergence of matter, our universe is a testament to the profound consequences of imperfection. Though we often view these events as relics of the distant past, the universe remains in a state of evolution. It continues to expand, cool, and transform. There may yet be undiscovered symmetries lurking at energy scales far beyond our experimental reach. And as the cosmic temperature declines further, new phase transitions may one day shatter these hidden symmetries, birthing unforeseen forces and altering the fundamental nature of reality itself. What if the fabric of reality extends beyond the 3 dimensions we know? What if space itself hides unseen directions, imperceptible to human senses, yet crucial to the fundamental workings of the universe? Could dimensions beyond length, width, and height be woven into the very structure of existence, influencing the cosmos in ways we have yet to comprehend? The history of scientific discovery is littered with ideas far ahead of their time, ideas so revolutionary that they languished in obscurity for centuries before their profound truth was finally acknowledged. Over 2,000 years ago, the Greek philosopher Democritus challenged the prevailing notion of matter as composed of earth, air, fire, and water. He proposed instead that all material objects were built from indivisible units, atoms. His atomic hypothesis was brilliant, but lacked the empirical evidence needed to convince his contemporaries. It would take more than 60 generations before atomic theory was firmly established by experimental science. Similarly, in 1783, English clergyman and scientist John Michell speculated on the existence of what he called dark stars, astronomical bodies so massive that their gravitational pull would exceed the escape velocity of light itself. If such objects existed, they would be entirely invisible, detectable only through their gravitational effects on nearby matter. This concept, fundamentally correct, would be forgotten for nearly 2 centuries until the development of general relativity and the subsequent discovery of astrophysical black holes in the 20th century brought it back into relevance. The trajectory of scientific ideas often follows a path of initial rejection, quiet dormancy, and eventual rediscovery. To the list of prescient yet long overlooked theories, we might add another, the notion that space itself harbors hidden dimensions. This radical idea was first put forward by mathematician Theodore Kaluza in the early 1920s and later explored by Albert Einstein. Kaluza extended Einstein's general relativity into a higher dimensional framework, proposing that our universe might include an additional spatial dimension beyond the familiar 3. His theory suggested that electromagnetism, the force governing light and charged particles, could be naturally unified with gravity if space were 5-dimensional. While compelling, Kaluza's proposal remained speculative, as no direct evidence for extra dimensions has yet been found. The theory was later refined and expanded upon, particularly in the context of string theory, which posits that fundamental particles are not point-like entities, but rather tiny, vibrating strings. These strings, according to the theory, require additional spatial dimensions, perhaps as many as 10 or 11, to be mathematically consistent. However, these extra dimensions are thought to be compactified, curled up at microscopic scales far beyond our current ability to detect. But how could we ever prove the existence of hidden dimensions? Scientists have proposed a variety of experimental approaches. If extra dimensions exist, they could influence the behavior of gravity at very small distances, a phenomenon that could be tested through high-precision measurements. Alternatively, high-energy particle collisions, such as those conducted at the Large Hadron Collider, might reveal the presence of extra-dimensional effects, producing exotic particles or deviations from standard physics. Like the atomic hypothesis and the dark star conjecture, the idea of hidden dimensions remains one of the most tantalizing frontiers in theoretical physics. If proven true, it would reshape our understanding of the universe, potentially unlocking deeper connections between the forces of nature and revealing a hidden structure underpinning reality itself. Whether through new mathematical insights, experimental breakthroughs, or technological advancements yet to come, the search for extra dimensions continues, an intellectual journey that may one day illuminate the profound mysteries of space and time. The 5th dimension, a hidden reality in space-time. The year was 1916. While Europe was being ravaged by the Great War, a conflict of unprecedented scale that consumed an entire generation, a different kind of battle was unfolding in the realm of theoretical physics, one waged not with bullets and artillery, but with equations and deep conceptual thought. At its heart was Albert Einstein, whose mind was fixed not on the transient destruction of war, but on the eternal structure of the universe itself. For over a decade, he had struggled to extend his revolutionary special theory of relativity, which had redefined space and time in 1905, into a new framework that could incorporate gravity. After many false starts and intellectual dead ends, Einstein finally triumphed, presenting his general theory of relativity, an elegant yet profoundly unintuitive reimagining of gravity not as a force, but as the curvature of space-time itself. General relativity transformed our understanding of gravity, recasting it in the language of geometry. Space and time, once thought of as rigid and separate entities, were now seen as a single, dynamic fabric that could bend and curve in response to mass and energy. Yet, as beautiful as this new theory was, it remained largely incomprehensible to many of Einstein's contemporaries. Its mathematical formulation was daunting, its implications subtle, and its experimental confirmation, though eventually achieved, was at first far from obvious. Among those who sought to understand and extend Einstein's work was Theodor Kaluza, a physicist born in the region of Silesia, then part of the German Empire. Kaluza's intellectual roots were steeped in the rich academic traditions of Königsberg, a city that had once nurtured the genius of Immanuel Kant. The world he grew up in would eventually be erased by the tides of history, Silesia absorbed into Poland, Königsberg transformed into Kaliningrad under Soviet rule, but his ideas would endure. Kaluza's approach to general relativity was bold and unconventional. He asked a simple yet radical question: what would happen if Einstein's equations were rewritten not for the conventional 4 dimensions of spacetime, 3 spatial and 1 temporal, but for 5? This was not an idle exercise in mathematical curiosity. If gravity was, as Einstein had shown, the result of spacetime curvature, then why restrict oneself to only 3 spatial dimensions? What new insights might emerge from considering a world with an additional hidden dimension? At first glance, such an idea seemed preposterous. The world as we experience it has 3 spatial dimensions, no more, no less. One can move forward and backward, left and right, up and down, but there is no evident 4th spatial direction in which one might move. However, Kaluza proposed a simple yet profound resolution. What if this extra spatial dimension was compactified, curled up so tightly that it was effectively invisible to human perception and experimentation? In this scenario, spacetime would consist of 3 large, extended spatial dimensions, alongside 1 minuscule, hidden dimension that remained beyond the reach of direct observation. With this assumption in place, Kaluza proceeded to rederive Einstein's equations for a 5-dimensional spacetime. What he found was extraordinary. The equations naturally separated into 2 distinct sets. One set corresponded to Einstein's familiar equations of general relativity in 3 spatial dimensions, preserving the known physics of gravity. But the second set was startling. It bore a striking resemblance to the equations of electromagnetism, the force governing electricity, magnetism, and light. In other words, Kaluza's extra dimension was not merely an abstract mathematical artifact. It provided a natural and geometric explanation for the electromagnetic force. The structure of Maxwell's equations, which had been empirically discovered in the 19th century, emerged seamlessly from the geometry of a higher dimensional space. This was an astonishing revelation. Gravity in 5 dimensions appeared to unify 2 fundamental forces of nature, gravity and electromagnetism, within a single framework. Recognizing the significance of his discovery, Kaluza submitted his findings to the Prussian Academy of Sciences, with none other than Albert Einstein himself acting as sponsor. The implications were profound. For centuries, physicists had sought a unified description of nature's forces, and here, in the fabric of higher dimensional geometry, lay an elegant solution. Yet, despite its promise, Kaluza's work failed to ignite widespread enthusiasm. It was a time of tumultuous change in physics, and general relativity, though a deep and sophisticated theory, was already being overshadowed by another intellectual revolution: quantum mechanics. The early 20th century was an era of creative destruction in physics. The once stable foundations of classical mechanics, built over centuries, were crumbling in the face of experimental discoveries that defied all prior expectations. The emerging quantum theory revealed a universe that was probabilistic, uncertain, and governed by bizarre rules fundamentally at odds with classical intuition. The brightest minds of the era, Heisenberg, Schrödinger, Dirac, and Bohr, were captivated by the mysteries of the quantum world, pushing the boundaries of knowledge in ways that seemed far more immediate and fruitful than the abstract considerations of extra dimensions. Moreover, general relativity itself was struggling for relevance. Despite its profound conceptual breakthroughs, its contact with experiment remained limited. The effects of gravitational curvature were subtle and difficult to measure, and the theory offered few tangible predictions that could rival the striking successes of quantum mechanics. If general relativity was already marginalized, then a version of it extended into an unobservable 5th dimension was even more so. Why, many physicists asked, Should they concern themselves with an invisible dimension when the quantum realm was teeming with tangible mysteries waiting to be unraveled? And so, Kaluza's idea, though brilliant, was largely ignored. For years, then decades, then nearly a century, the notion of extra dimensions remained a backwater of theoretical physics, an elegant but speculative hypothesis that found little experimental support. Yet, despite its neglect, the seeds Kaluza had sown would not be forgotten. As the 20th century gave way to the 21st, new developments, particularly in the realm of string theory, would resurrect his vision in a dramatic way, casting extra dimensions not as a mathematical curiosity, but as a fundamental aspect of reality itself. What Kaluza glimpsed in the early 20th century was perhaps a shadow of a deeper truth, one that modern physics is still struggling to fully comprehend. His work was a testament to the power of imagination in science, to the idea that even the most audacious hypotheses can, given time, prove to be the keys to unlocking the deepest mysteries of the cosmos. Today, as physicists continue their quest for a unified theory of nature, the echoes of Kaluza's fifth dimension still resonate. Reminder that sometimes the answers we seek lie not in what we can see, but in the hidden structures beyond our perception. A theory of strings, the birth of extra dimensions in physics. Nestled within the majestic Colorado Rockies lies the town of Aspen, a retreat for the affluent, where luxurious residences merge with breathtaking natural beauty. Yet, beyond its social exclusivity, Aspen hosts an intellectual enclave, the Aspen Center for Physics. Here, amidst the tranquil surroundings, some of the brightest minds in theoretical physics convene to exchange ideas, explore profound questions, and confront the mathematical complexities of the universe. It was in this setting, during the summer of 1984, that two physicists, Michael Green of Queen Mary and Westfield College, University of London, and John Schwartz of the California Institute of Technology, made a breakthrough that would redefine the landscape of modern physics. As thunderstorms rumbled across the mountains, Green and Schwartz presented a solution to a fundamental inconsistency in theoretical physics, a problem that had long been deemed an insurmountable barrier to the viability of extra dimensions. The repercussions of their work would be profound. What had once been considered an esoteric and largely disregarded idea was now thrust into the spotlight, igniting a revolution in theoretical physics. For much of the 20th century, the notion of extra dimensions had been largely dismissed as a speculative detour, lacking empirical motivation. However, in the early 1970s, a peculiar and largely overlooked framework, string theory, began to suggest that extra dimensions were not merely an abstract possibility, but a necessary condition for mathematical consistency. Despite its promise, string theory was an outlier, viewed with skepticism by the wider physics community. Its foundational premise was deceptively simple. Consider a one-dimensional object, such as a taut violin string or a crackling whip. Elevate its description to a relativistic regime where its endpoints move at the speed of light. Then, impose the principles of quantum mechanics. The resulting theory was unlike anything physicists had encountered before. The origins of string theory trace back to 1968, when Italian physicist Gabriele Veneziano sought to explain the strong nuclear force, the interaction that binds protons and neutrons within atomic nuclei. In a summer marked by social upheaval, student protests, and cultural transformation, Veneziano discovered an intriguing mathematical function that seemed to encapsulate key properties of the strong interaction. Over the next 5 years, physicists explored this approach in depth, hoping to construct a comprehensive theory of the strong force. However, two formidable obstacles emerged. First, the particle spectrum predicted by string theory did not align with experimental data. More critically, the theory exhibited a fundamental inconsistency. Calculations involving probabilities failed to yield a sum of one unless the universe contained 6 additional spatial dimensions beyond the familiar 3. By the mid-1970s, string theory was widely regarded as a failed endeavor, destined to join the graveyard of discarded hypotheses. Yet, for a small cadre of physicists, including Green and Schwartz, certain mathematical peculiarities hinted at a deeper significance. The theory exhibited a surprising degree of internal coherence, with subtle cancellations appearing in calculations that defied expectations. Was it possible that string theory had been misapplied? Could it be that instead of describing the strong force, it was, in fact, the long-sought quantum theory of gravity, the missing piece in the grand puzzle of fundamental physics? This proposition, at the time, was met with overwhelming indifference. Quantum gravity was an esoteric pursuit, occupying only the fringes of theoretical inquiry. String theory, already marginalized, seemed an unlikely candidate for unifying the fundamental forces. Moreover, any attempt to incorporate the Standard Model, the prevailing framework describing known particles and interactions, into string theory appeared to lead to fatal inconsistencies. Once again, the problem arose. Probability calculations were fused to sum to one, signaling a breakdown of the theory at a fundamental level. Then came the breakthrough in Aspen. Green and Schwartz uncovered a missing component in these calculations, a subtle mathematical term that had previously gone unnoticed. When this term was included, the inconsistencies vanished. The result, now known as the Green-Schwartz anomaly cancellation, established string theory as a mathematically consistent framework, paving the way for its resurgence. For the first time, a quantum theory incorporating gravity did not suffer from fatal logical flaws. It was a moment of profound significance, its impact mirrored by the storm that raged outside the conference hall. With this discovery, the perception of string theory underwent a radical transformation. What had once been an obscure and disregarded field became one of the most active frontiers of theoretical physics. The requirement of extra dimensions, previously seen as an absurdity, was now taken seriously. If string theory was to describe the fundamental nature of reality, then our universe must possess 10 dimensions, 3 of space, 1 of time, and 6 compactified dimensions hidden from our everyday experience. The challenge now is to bridge the gap between this higher dimensional reality and the observable 4-dimensional world governed by the Standard Model. The notion that all known particles and forces arise from the vibrational patterns of fundamental strings captivated physicists. No longer was string theory merely an oddity. It was a potential theory of everything, capable of unifying gravity with the other fundamental interactions. The quest for quantum gravity, an endeavor that had eluded even Einstein in his final years, was reinvigorated with newfound urgency. The intellectual landscape of physics had been reshaped overnight, and the race to explore the implications of extra dimensions had begun in earnest. What transpired in Aspen in 1984 was more than a technical resolution to a mathematical inconsistency. It was a pivotal moment in the pursuit of a deeper understanding of the cosmos. The echoes of that storm, both literal and metaphorical, still reverberate through the halls of theoretical physics, where the quest to unravel the ultimate nature of reality continues to this day. Visualizing the invisible, the enigmatic geometry of Calabi-Yau manifolds. In 1984, while enjoying the serene expanse of the Pacific Ocean in San Diego, I received an excited phone call from my colleagues Andrew Strominger and Gary Horowitz. The urgency in their voices was unmistakable. String theorists were constructing new models of the universe, and they needed to confirm the existence of a special class of mathematical objects, Calabi-Yau manifolds. Their significance was profound. These geometric structures might hold the key to the hidden dimensions of reality. Mathematics has long been the foundation for understanding space and shape, from Pythagoras' theorem to Euclidean geometry and beyond. But the geometries we learn in school, circles, planes, parallel lines, are mere shadows of a deeper, richer mathematical world. Some structures defy intuition. Mobius strips, Klein bottles, and Roman surfaces challenge our perception of space. And yet, they are still comprehensible. What, then, are we to make of the 6 additional dimensions proposed by string theory? Dimensions so small, so curled up, that they remain invisible to direct observation. To answer this question, we must ask, what possible shape could these 6 extra dimensions take? Are they constructed from familiar elements like straight lines and spheres? Or are they altogether alien, possessing bizarre and intricate topologies? Among the many candidates, Calabi-Yau manifolds have emerged as the most compelling. Named after mathematicians Eugenio Calabi and Xingtu Miao, these spaces possess a delicate and intricate structure governed by the principles of complex geometry. Here, complex refers not just to their intricacy, but to their deep connection with complex numbers, which extend beyond the familiar realm of real numbers to include the elusive imaginary unit, defined by the equation. Mathematically, Calabi-Yau manifolds are remarkable. They contain hundreds, sometimes thousands, of higher dimensional analogs of wholes, forming a topological landscape of almost inconceivable complexity. But why have they captivated the interest of physicists as well as mathematicians? The answer lies in the fundamental laws of the universe. The equations of Einstein's general relativity dictate how space-time can curve under the influence of mass and energy, imposing stringent constraints on the geometry of any viable physical theory. Astonishingly, Calabi-Yau manifolds naturally satisfy these equations, making them an ideal candidate for compactifying the extra dimensions predicted by string theory. Yet, general relativity alone is not enough. It is a classical theory, silent on the effects of quantum mechanics. Often, when quantum fluctuations are introduced, elegant classical solutions unravel under the strain of uncontrolled infinities. This is where Calabi-Yau spaces offer a crucial advantage. They preserve a powerful symmetry known as supersymmetry. This symmetry acts as a safeguard, ensuring that the catastrophic infinities arising from quantum effects cancel out precisely. Without such protection, the extra dimensions of string theory might collapse under the weight of quantum instability. When physicists first explored these manifolds in the 1980s, only a handful of examples were known. There was hope that a unique geometry would emerge, providing a direct pathway from string theory to the standard model of particle physics. But as computational power grew, so too did the catalog of possible Calabi-Yau spaces. What began as a few examples multiplied into billions. Instead of a single, elegant solution, physicists found themselves grappling with a bewildering landscape of possibilities. This presents a profound challenge. Our everyday experience suggests that space is three-dimensional, extending through length, width, and height. The idea of additional dimensions is alien to intuition. If these extra dimensions exist, they must be exceedingly small, perhaps a quadrillion times smaller than an atom. How, then, can we ever hope to detect them? And more fundamentally, what does it even mean to speak of dimensions we cannot see? These questions remain unanswered, but they drive one of the most ambitious quests in modern physics. If Calabi-Yau manifolds truly shape the unseen fabric of reality, then understanding them is not just an exercise in abstract mathematics. It is a glimpse into the deepest architecture of the cosmos. Where are the hidden dimensions? What does it truly mean to see something? Perception, in its essence, depends on the interaction between light and matter, a fundamental principle that governs our ability to discern the world around us. A well-known anecdote about Richard Feynman, whether fully factual or not, illustrates this point vividly. As the story goes, Feynman was examining a PhD student whose thesis involved quantum gravity, a subject deeply entrenched in mathematics. Concerned that the student had lost sight of the physical meaning behind his equations, Feynman posed a simple yet revealing question: what is the wavelength of visible light? The student hesitated before guessing incorrectly that it might be about a meter. In response, Feynman walked towards him and asked, "Do I look blurry to you?" The fundamental reason we can see each other and discern fine details in our surroundings is that the wavelength of visible light is roughly a millionth of a meter. Objects significantly larger than this scale do not blur when viewed in visible light, while those smaller, such as atoms, become imperceptible. Atoms, though integral to our physical world, are about 1,000 times smaller than the wavelength of visible light, rendering them invisible to direct human observation. However, their existence is irrefutable, as we constantly experience their effects. The solidity of a chair, the resistance we feel when touching an object, is the cumulative result of countless atomic interactions governed by electromagnetic forces. This fundamental principle leads us to an even deeper question. If extra dimensions exist, how might they manifest in our observable universe? If space possesses a hidden geometry at minuscule scales, what effects could it impose at larger, detectable scales? To answer this, we must first grasp the essence of dimensions. We are intuitively familiar with three spatial dimensions, which define the directions we move in and allow us to label the positions of objects. A one-dimensional world, such as a straight line, requires only a single coordinate to specify a position. A two-dimensional plane requires two coordinates, while our familiar three-dimensional space requires three. But what about 4, 5, or even 10 spatial dimensions? How can we conceptualize spaces beyond our perceptual experience? A useful analogy involves an ant traversing a plant vine. To the ant, the vine appears as a one-dimensional path. It can move forward or backward along its length. Yet if we zoom in with a microscope, we reveal the vine's two-dimensional surface, complete with microscopic structures the ant cannot perceive. Similarly, if extra spatial dimensions are sufficiently small, we, along with all our technology, may be too large and coarse to detect them directly. The fundamental strings of string theory, however, are hypothesized to be small enough to navigate these hidden dimensions. This leads to another crucial question. Even if we cannot directly perceive extra dimensions, could we still infer their existence through indirect effects? Consider how we detect atoms, not by sight, but by their influence on the macroscopic world. A similar principle applies to extra dimensions, which may leave an imprint in the form of new particles. According to general relativity, the presence of extra dimensions alters the mathematical structure of space-time, giving rise to new quantum excitations. These excitations correspond to particles, much like how a photon, the fundamental quantum of light, arises from the electromagnetic field. The complexity of an extra-dimensional space determines the number and properties of these emergent particles. The more intricate the topology of the hidden dimensions, the greater the number of associated particles. Among the most intriguing of these particles are moduli. These particles encode information about the size and shape of extra dimensions, making them key indicators of extra-dimensional theories. If moduli exist, their properties should be observable in high-energy physics experiments. However, producing moduli in particle colliders poses an immense challenge. Unlike particles that interact via the strong or electromagnetic forces, moduli are tied to gravity, a force so weak that its effects are negligible in laboratory conditions. For perspective, consider how easily one can lift a small object against Earth's gravitational pull. This simple act demonstrates that electromagnetic forces are vastly stronger than gravity, making moduli exceedingly difficult to detect using conventional methods. The weakness of gravity implies that moduli, once created, could have exceptionally long lifetimes. While particles interacting by the strong force decay almost instantaneously, gravitationally interacting particles could persist for extended durations, even years. Thus, if moduli were produced in the early universe under extreme conditions, they could still be present today, offering a window into the structure of extra dimensions. The challenge, then, is to determine how we might detect these elusive particles. If colliders like the Large Hadron Collider cannot produce them, could they still leave detectable traces elsewhere? The early universe, with its extreme temperatures and densities, may have provided the conditions necessary for moduli production. If so, remnants of these particles could influence cosmic phenomena, such as the distribution of dark matter, the behavior of cosmic microwave background radiation, or subtle modifications to gravitational wave signals. The quest to uncover extra dimensions is thus intertwined with the broader pursuit of understanding the universe's fundamental structure. While our senses may be limited to 3 spatial dimensions, the mathematical and physical implications of higher dimensional spaces continue to shape our deepest inquiries into the nature of reality. If extra dimensions exist, their signatures, encoded in the form of particles, cosmological imprints, or subtle gravitational anomalies, may yet reveal themselves to those who seek to unveil the invisible fabric of the cosmos. Hunting for evidence at the beginning of time. At the dawn of time, it is widely believed, though not yet known with absolute certainty, that the universe underwent a brief yet astonishingly rapid phase of cosmological inflation. This period saw space itself expand exponentially, growing at an almost incomprehensible rate. In a fraction of a second, far shorter than the time required for light to traverse an atomic nucleus, the universe is thought to have doubled in size approximately 80 times over. A region initially smaller than the nucleus of an atom would have ballooned to a scale many orders of magnitude larger than the Earth itself. As inflation ended, the colossal energy driving this expansion was transferred into the production of particles, creating a seething cauldron of fundamental components. This phase, known as reheating, flooded the cosmos with energetic matter, setting the stage for the formation of everything that would follow. Crucially, this energy is not merely an abstract quantity. In Einstein's theory of general relativity, energy and geometry are deeply intertwined. Gravity is not a force in the traditional sense, but rather the manifestation of how mass energy warps space-time. Within the framework of extra-dimensional theories, particles known as moduli, quantum excitations of the geometry of hidden spatial dimensions, could have been among those generated during this post-inflationary epoch. If moduli do exist, then a portion of the inflationary energy would have naturally been transferred to them. They would have been produced abundantly, lingering within the cosmic maelstrom for an extended duration due to their exceptionally long lifetimes. Unlike other particles that rapidly decayed into more stable forms, moduli could have persisted far longer, coming to dominate the energy density of the universe for a fleeting but significant moment. For a microsecond, a relative eternity in the language of early universe physics, almost all the universe's energy may have been stored within moduli, the whispering echoes of extra dimensions manifesting in physical reality. To understand why these particles would be so influential, consider the ringing of a great bell. Upon being struck, the bell resonates with an orchestra of frequencies, a rich combination of harmonics that together define its tone. As time passes, the higher harmonics fade, leaving only the longest-lasting resonances behind. Similarly, in the early universe, the longest-lived particles would be those that remain once all else has decayed. Estimates suggest that a yoctosecond after the Big Bang, most unstable particles would have vanished. Yet moduli, impervious to most interactions, might have survived for nearly a full microsecond, a momentous interlude in the cosmic timeline. But what would this mean for the evolution of the universe? Although energy is conserved, its form can change. When moduli eventually decayed, their mass energy would have been released primarily as relativistic particles such as photons, the fundamental quanta of light. However, the nature of these decays has profound implications. As the universe expands, relativistic waves such as photons experience redshift due to the Doppler effect. Just as an ambulance siren shifts to a lower pitch as it moves away, so too does the wavelength of light stretch in an expanding universe. The energy of each photon is directly proportional to its frequency. As expansion continues, the photons lose energy. Moduli, however, would not experience such effects. Their energy is stored in their mass, making them unaffected by redshift. While the universe stretched, moduli would have remained, slowly decaying, outlasting other sources of energy, and leaving an indelible imprint on the cosmic fabric. If such an epoch occurred, it fundamentally alters our perspective on how we might detect moduli today. These elusive relics of extra dimensions, once thought to be beyond the reach of experiment, might instead have left a tangible legacy, a signature encoded in the observable universe. The key to their detection lies in their eventual decay. Moduli, despite their extreme lifetimes, do not live forever. When they finally decay, they deposit their energy into known particles, those that comprise the familiar standard model of physics, and potentially into exotic, undiscovered forms of matter. One of the most intriguing possibilities is that moduli decayed into axions, hypothetical particles that, while weakly interacting, are nonetheless predicted to exist. If a modulus were to decay into two axions, each would inherit half of its energy and travel at near-light speed through space. Unlike other particles, axions interact so weakly that they would have streamed freely from the early universe to the present day, forming an invisible, universe-wide background of radiation. Such a relic background would be difficult, but not impossible, to detect. One promising approach relies on the fact that axions, in the presence of strong magnetic fields, have a small probability of converting into photons. This process, known as the Primakov effect, offers a potential observational window into the hidden physics of extra dimensions. By studying regions of space where magnetic fields are particularly strong, such as in the vicinity of neutron stars or within specially designed laboratory experiments, we might uncover the telltale signs of axions, and by extension, the moduli from which they arose. The prospect of detecting such a cosmic axion background is reminiscent of another long-sought relic of the early universe, the cosmic neutrino background. Although neutrinos are ubiquitous, estimated to number in the hundreds per cubic centimeter across the cosmos, they interact so weakly that their detection remains a formidable challenge. Even the most sensitive detectors, designed to observe high-energy neutrino interactions, struggle to record more than a few events per year. Yet, if we are clever, if we refine our methods, we may one day capture traces of these elusive messengers from the universe's infancy. A century ago, Einstein's theory of gravity revolutionized our understanding of space and time. Around the same time, the idea that our universe might contain hidden dimensions also emerged, a notion as tantalizing as it is elusive. If extra dimensions do exist, they are not merely abstract mathematical constructs. They would permeate every point in space, shaping the fundamental laws of physics in ways we are only beginning to grasp. Their presence would be hidden from our direct perception, much like trying to count grains of sand while wearing thick gloves. Yet, through the whispers of moduli, through the traces left behind in the cosmic afterglow, we may one day discern the structure of these hidden dimensions. Perhaps, with the right tools and the right insights, we will unveil a universe far grander, richer, and more intricate than we have ever imagined.